All right, so welcome to the second video for section 4.2, which I believe is the fifth video for chapter 4. So I pause, copy down this panel, and then I'll start chunnering. All right, so nothing new in this video, really. We're simply going to apply the result of the central limit theorem to one particular distribution, the binomial distribution, because it's a common one that crops up. So let's suppose I have a random variable x that's binomially distributed with n being 300 and probability of success p. So that means I'm running 300 independent trials. Each trial has probability of success p, and x records how many successes I had. So x was 0 for a failure, we had 0 for failure, 1 for success. So x is the total number of successes. All right, well, recall that a binomial distribution is simply a sum of Bernoulli's. So x is really a sum of 300 random variables that are independent and identically distributed. Each of them follows a Bernoulli distribution with probability of success p. And recall that a Bernoulli distribution was just one trial with probability of success p. So x sub I is either 0 for failure, 1 for success. All right. So we see that x, a binomial random variable, is actually a sum of independent and identically distributed Bernoulli's. And that's custom built for applying the central limit theorem too. Laying up a bunch of independent and identically distributed random variables. Okay. All right, so let's do an example here. I've got a fair coin. I'm going to toss it 300 times, and I'd like to approximate the probability of getting at most 160 heads. Okay, so each of these coin flips, x1 through x300, is Bernoulli, and it's a fair coin, so there's a 50-50 chance of heads or tails. Okay, well, that means the expected value of each x sub I is 0.5. If you remember your Bernoulli random variable or Bernoulli distribution facts. And the variable of each x sub I is p times 1 minus p, which would give us 0.25 for the variance. Sorry, the variance. All right, and we obviously have n equals 300. So I'm looking for the probability that the sum of these Bernoulli trials adds up to something less than or equal to 160. So what I'm going to do is I'm going to try and get an x bar out of this thing, because that's what the central limit theorem speaks to. So to get an x bar out of this thing, I'm simply going to divide by 300. So that's the average success rate. Total number of successes divided by total number of trials. Okay, so I'm going to divide both sides by 300. That gives me an x bar and 160 over 300. And then I know that x bar is approximately normally distributed. Okay, so I'm going to subtract 0.5 and divide by, because that's the expected value of the xi, and divide by the 0.25 over 300 square root, the standard deviation. And that's just straight from the central limit theorem. Divide by sigma over the square root of n. Sigma is the square root of 0.25. Square root of n is the square root of 300. Okay, so I do that on both sides. And the central limit theorem says, well, now you've got approximately a standard normal variable on the left-hand side. So that's a z. Right-hand side cranked out to 1.155. And I give that to R to calculate via standard normal distribution, and I get 0.875. Right? So there's the central limit theorem applied to binomial. Okay. Now, you might be slightly confused where the 0.5 and the 0.25 over 300 came from, but just look back at that central limit theorem. The mu and the sigma over root n are exactly as they should have been from here via the central limit theorem. Okay. All right. Well, having said that, you might find it useful to have an explicit interpretation of the central limit theorem applied to a binomial or the Bernoulli's. Okay. So that's what this corollary says. So pause, copy, and I'll chunner. Okay. So a corollary to a theorem is simply an equivalent way of stating the theorem or applying the theorem to a very specific case. Nothing has to be proven because it's simply an application of the theorem. The theorem proves something in general. Now we're applying it to a specific case. So here we're applying it to the case where x is binomially distributed. So it's a binomial random variable, n trials, probability of success in each trial is p. And I'm going to define x divided by n. Normally I call that x bar. For this, I'm going to call it p hat, the proportion of success. Okay, because this binomial distribution has a specific interpretation of that. Now, if both n times p and n times 1 minus p are large, greater than 10 is what we said, greater than or equal to 10 is what we said, then the sampling distribution of p hat is approximately normal. Probability of success p, so that's the mean, and the variance is p times 1 minus p over n. And this is exactly what the central limit theorem said. All right. There's my mean, my mu for each of these xi's that constitutes x. P times 1 minus p was the variance of each of the xi's. And then I divide it by n as directed by the central limit theorem. Okay. All right. So that would mean the standard deviation is the square root of that variance. Or if you don't like that one or whatever, we could also get the sampling distribution of x. So not x over n, but just x. And that is also approximately normal. Since I'm not dividing by n, I multiply my mean by n, and I multiply my variance by n squared, right? And we can crank through that. X is simply n times x over n. So the expected value of x is n times the expected value of x over n. And the variance of x is simply n squared times the variance of x over n. So when I drag an n out of the expected value, it comes out as an n. When I drag it out of the variance, it comes out as an n squared. And then these two things eventually give us the np and the n times p times 1 minus p when applied to those two guys. Okay. All right. Now you see why I don't write on the board in class. Okay. So let's apply this to another example, see how we go. All right. So pause. Copy it down, press play, and scooch this over just a bit. Okay, so this is example 4.11 from the book, 4.11. So I've got x is binomially distributed with 120 trials and probability of success of 0.3 in each trial. And that would approximate the probability that x is less than or equal to 25. So if there's 25 or fewer successes, okay? Now, let's see. Some information. The expected value of x is n times p. So that's 120 times 0.3, which is 36. And the variance of x is np 1 minus p. So those are just binomial facts, binomial distribution, mean and variance. And so I get the variance of x is 25.2. Now, because I know what's sort of coming up in the moments to come, I'm going to take these two pieces of information and calculate the expected value of x over 120. So I drag out the 1 over 120, get a 0.3. Variance of x divided by 120, drag out the 120 as 1 over 120 squared. It becomes 0.04183 squared. So 0.04183 is my standard deviation. And I also observed that n times p and n times 1 minus p are both greater than or equal to 10. Okay. All right. So by the corollary, x bar, which we could also call p hat, the portion of successes, equaling x over 120, is approximately normal with mean p and variance p 1 minus p over n. Okay. Or that variance, I'm going to state it as the standard deviation squared. Okay. And that's standard deviation right there. Okay. So these two pieces of information got plugged in for the mean and the variance of the normal distribution for x bar. Great. All right. So let's actually tackle the problem. I'm trying to calculate probability x is less than or equal to 25. So I'm going to divide both sides by 120 to create the x bar, right? I know x bar is approximately normally distributed, and I know its mean and its standard deviation. So I'm going to subtract its mean, and I'm going to divide by its standard deviation on both sides. Central limit theorem then tells me that this expression on the left here is approximately standard. So replace it with a z. It's now an approximation. Cranked out the value on the right. If I need to calculate the probability that the standard normal is less than a negative number, I calculate 1 minus the probability that the standard normal is less than or equal to its positive equivalent. There's my bell-shaped curve. There's 0. Let's just say there's -2. If I wish to calculate that area, that is the same as calculating the right tail. So I can simply calculate 1 minus all of that. So 1 minus the probability z less than or equal to 2. Okay. So hopefully you recall doing that kind of stuff in 313. Otherwise, let me know. We can crank through a couple in class and you'll quickly remember it. Okay, so let me know if you need me to run through some examples. So anyway, I crank it out, I give R that value, and I get 0.014, okay, as my approximation for the probability that X is less than or equal to 25. Now, this is all fine and dandy. I didn't need a whole lot of technology to do it, and I could have approximated this value from the standard normal table. However, in the world of wonderful modern computing, I will observe that R has no trouble calculating this probability exactly. It can simply calculate the probability that X is equal to 0 successes in the 120 trials, plus the probability that X has 1 success in the 120 trials all the way up through 25, using the binomial probability mass function. 120 trials, choose the number of successes, 0.3 to the number of successes, 0.7 to the number of failures, okay? So R can crank that thing out exactly, and it got 0.0159, which is pretty close to us, okay? And perhaps in class, I'll show you the R code for this, otherwise it is in the chapter. Okay,